All right, everybody. Hello, this is Jim Malis, and I want to help everybody out here. I'm doing this particular video. It's about intermediate algebra, but it's going to help a number of people, I think. I'm going to probably use it in different circumstances. For those of you in my MATC course regarding algebra, intermediate algebra, here are some, I'm going to do a series of old practice exams that I'm not sure if they're still using them. They may not be using them. They were done by some very hard-working, intelligent people who would put these together, and I'm going to solve them to a large degree, start to finish. I don't know if I'm going to do every single problem, but I might try to do just that, actually, as we go. So give you some background on this thing. So there's going to be, regarding what we're doing, this will be the first of the old practice exams, and there are 3 other ones. So it's practice exam number 1, old practice exam number 1, old practice exam number 2, and old practice exam number 3. And practice exam number 4 is a comprehensive final exam. These are old exams that were used for an old course, but guys, you know what? Math is math. Mathematics is mathematics. It's the stuff we, if you know math, you know math. It doesn't matter from what textbook it's coming from. So anyway, let's take a look and let's figure this thing out. There are and I posted this for I'm going to post this for my MATC students, and I'm likely going to post this for my UWM students as well. Just so in case they want to look at a little background in some of the basic mathematics, you want to, for personal enrichment, you might want to be looking at something like that. I guess there's a number of things that you can say. Let me say them. Let's figure out how we're going to do this whole thing, guys. There was, before I get into the old practice exam number 1, let's look at the fact that x to the 0 is equal to 1, x to the 1 is equal to x, x to the m times x to the n equals x to the m plus n. X to the m divided by x to the n is x to the m minus n. If you exponentiate an exponentiated quantity, you multiply the exponents. If you exponentiate a product, you bring the exponent inside and hit every item in the product. If you exponentiate a quotient, you bring the exponent inside and you exponentiate each, so if you exponentiate a product, you exponentiate a product, you exponentiate each factor in the product. Exponentiate a quotient, you exponentiate each item that is in the quotient, so on and so forth. If you take something to the negative power, which may be a positive number, may be a negative number, that's something to kind of watch out for. It comes out to this. There's a lot here, guys. These are some basic laws of exponents. People think they know this stuff really well. They probably do. They probably do a lot of times. But I will tell you something. I'll tell you something for sure. Know this, but more important than knowing this, or as important than knowing this, knowing what to do, knowing what not to do, knowing the do's and don'ts. This is true. This is true. It works that way, but if you were adding 2 items and then exponentiating, that's not going to be this. People think, oh, it should be. It was over here. No, it's not going to work that way. Here, for example, you had this, and you took it like that. That's going to be this. No, it's not. So whenever there's addition and or subtraction going on, the process is much more difficult to do something like this. Notice all of these entail straight out multiplication or straight out division or straight out multiplication and or division going on put together. If you're adding, it doesn't work like this. You have to use, for problems like this, you have to use some really beautiful mathematics associated with the binomial theorem and even a more general look to the binomial theorem. Something more general than the binomial theorem is the multinomial theorem. Some really beautiful mathematics that's out there, guys, that explains what this really is. It's certainly not that. That's why I said it's not equal to it. So there's a lot of do's and don'ts there. There's a lot to say. Time constraints kind of put me in a weird spot, you guys. But the big thing is, if you were ever, one thing I think everybody's got to kind of remember, when do you distribute, when do you not distribute? You always use the distributive property. You always use the distributive property when there's addition and or subtraction going on within a bracketed or parentheses quantity. If I'm going to multiply or divide across a bracketed or parentheses quantity, if I'm going to multiply or divide across a quantity that has addition and or subtraction going on, I will distribute the multiplication or division. If there's no addition or subtraction going on, you will not distribute. It's that simple. If I'm saying to you, for example, if I had so much to say, I mean, guys, it's so little time to say it sometimes, I guess you could say. If I had this and I had t right here, the t would go here, 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 and you'd get t times a, t times b, t times c. Absolutely true. If you had this, the t just hits one of them. The other two are left alone. Do you want to put the t next to the b or t next to the c? That's fine, but you won't distribute and hit everybody. Here you will distribute and hit everybody. If this is a minus. Over a plus and a minus, the distribution takes place like that. It's the same thing with division. Say you had something like this and you divided it by t. You could write it like this. The t goes here, here, and here. So we got this. Now what if you had this? How would you do this one? This one, it would just be this. Or it would just be this. Or it would just be this. But it's not going to go to all three. It's going to go just to one of them. It's just going to go to one of them, no matter how you do it. And this happens all over the place. And I have a handout for you guys posted online called Discussing, pertaining to some of the concepts useful in the study of polynomials, laws of exponents. I think the big thing I say there, I think I say some algebra. I have it listed as some algebra when you look at it. Some do's and don'ts of exponents. So the do's and don'ts are a big thing. And here's some of them. So if you got something like this, if you got 8x to the third, y to the fifth, z to the ninth, times, 9x, y, like that, you are not going to distribute. You're going to go numbers with numbers and be done. Numbers with numbers. 8 times 9, 72. X to the third times x to the 1. Did we say x is x to the 1? Y is y to the 1. Add the exponents. Don't go 1 times 3 and get 3. Go 1 plus 3 and get 4. Y to the fifth, y to the 1. 5 and 1, 6. Z to the ninth, there's nothing being with it. Write it down. Notice though, I went letters with letters. I went like letters. I went like letters with like letters. Numbers with numbers, like letters with like letters, and I obeyed what I had to do. It's a different dynamic if the problem would have been something like 8x to the third, y to the fifth, z to the ninth, and then you were multiplying it with 72x to the fourth plus y to the sixth plus z to the ninth. So if you're looking at something like that, Take this whole, now, if there's addition and or, what the heck, let's throw a subtraction in here. If nothing's in front of a letter, put a 1. If nothing's in front of a letter, put a 1. Minus y to the 6th is plus a negative y to the 6th. Take this guy and go here, and go here. Wow, I picked some really, interesting numbers, I guess you could say. I made one up here. So 8 times 72 is 576. And so I'm doing this kind of on the fly, guys, obviously, but 8, let me see here. I got this. This guy's going to get distributed. There's no two ways about it. This guy's going to get distributed. So you're going to say 8 times, you're going to say 8 times 72, let me just try to think here. 560 plus 16, 576. Numbers with numbers, got it. This guy, x to the 3rd, x to the 4th, 3 and 4, 7. Tack these guys on there. It's a multiplication. They come around for the ride. That's it, you're done. You got him. Plus a negative. Negative 1 times 8 is this. You got x to the 3rd. You got y to the 6th times y to the 5th. Go like with like. 5 and 6 is 11. Z to the 9th. 1 time, now go here. 1 times 8. Leave this guy here. You're not doing distribution there. You've already done the distribution. Z to the 9th times z to the 9th. 9 and 9 is 18. Okay, there it is. You don't do, here we go. You got this. You got this. You got this. Yeah, that came right from that. Here you do distribution. Once you've done the distribution, you're done. You're not going to take this guy and start distributing it some more. There's nothing to distribute here. There's no brackets or parentheses, but more importantly, not only is there no brackets or parentheses, there's no addition and or subtraction within brackets or parentheses. No addition and or subtraction within brackets or parentheses. No addition and or subtraction within brackets. Straight out multiplication. Leave it alone. No more distribution. You did the distribution. You did the distribution. It was that right there. It got you there. You cannot simplify this any further. You got to have like terms. If you got 5x squared y to the 3rd z plus negative 20 x squared y to the 3rd z. Oh, these are, if the tail end is the same, add the numbers together and keep the tail end. These are like terms. 5 boxes plus the loss of 20 of the same boxes. Where are you net? Net? You had 5 boxes, you gained 5 boxes and you lost 20 boxes. You gained 5 boxes and then afterwards you lost 20 boxes, despite the fact that you initially gained 20 boxes. You initially gained 5 boxes, then you lose 20 boxes. Gain 5, lose 20, I'm down 15. Letters and exponents always remain unchanged when you add or subtract. Letters and exponents always remain unchanged when you add or subtract quantities. Letters and exponents always remain unchanged when you're adding or subtracting quantities. And you can't simplify unless you have the exact same letters and exponents. Exact same letters associated with the exact same exponents. Simple as that. Here you simplify it. If they would have altered this, period, end of the story on that one. Now, if they would have altered this a little bit, if this would have been a 3 and that a 2, I'm going to leave that here. I'm going to leave that as is. If you want to go here, go ahead and do so. You're done. You cannot simplify that. Do not say that you cannot add these. You certainly can add them. You just did add them. You just can't simplify them any further. Why can't I simplify them any further? There's x's, y's, and z's. There's a 3, there's a 2, there's a 1. This is to the 1 power. There's a 1, 2, 3. There's a 1, 2, 3. Yeah. The numbers are not in the exact same place. These aren't like terms. You've got to have the exact same exponents associated with the exact same letters. The term has to be identical. same letters, same location exponents. Same location of the exponents, same letters, and same location exponents. You're done. You can't do anything more than this. Earlier you saw what I erased. This is the good thing about being on tape. You can always go backwards and look at what I did. Okay? So there it is. There it is. You got something looking like this, and they do stuff. I mean, if you were going to multiply some quantity, let's say 5xy plus a negative 9z times, 10x squared y to the third z minus 50 xy plus 9. Say I gave you this. Well, that's a different, it's a little bit of a different story. See what we can say here. Let me get some of this stuff out of here, guys, and we'll figure out. We're trying to straighten some stuff out. We, had a little bit of our challenges trying to get this stuff taped. It's a tough situation with obviously everything going on. I mean, okay, you saw what we did there, guys. Get this out of here. Unclutter this a little bit. Okay, let's see what I did here. I think I managed to screw this up, guys. That was a 9 there, wasn't it? I think. I'm talking to one of my students here, or kind of like a student. It's a long story. Anyway, so doesn't matter. We got it to here, guys. So we got this. What's going on here? Can I ask you a question? Minus 50xy is plus a negative 50xy. Fair enough? Okay. Let's see what we got here, guys. I got markers all over the place. If there's an addition going on, is that visible okay? That's okay, I think. You see that okay? Not bad. Okay, it's not great, but all right. You're going to take, if you're doing this, you're going to do distribution twice. You're going to pretend this guy's not here. You're going to pretend this guy ain't there. And just take this guy and go here, here, and here. I don't exactly like that marker, but then you're going to take this guy, go here, here, here. So you're going to do the distributive principle twice. It's pretty simple that way. And let's see what happens. Let's take our time on this. Got 5xy. Now this guy's doing the job. He said he's doing the job. He's going here, and he's going to come around and go here. He's going to go here, and he's going to go there. You're going to distribute the 5xy. (10x squared y to the third). Let's see what we got here. 10x squared y to the third z. Again, I always manage to pick something that's going to take the better part of a year to do. Well, let's see what we got here. So I took this guy, brought him across. Got that. Okay. There it is. That's the first iteration of what goes on, you guys. The first iteration of what goes on. Let's do the other one. Then we got negative 9z times, here we go. Distribute that guy now. There it is. Yeah, it's quite a bit. But that's how you do it. You did the distribution. Why do you do distribution? You do distribution because there's addition and subtraction symbols. There's addition and subtraction symbols everywhere. I don't want you to worry about this, guys. A minus B is A plus the opposite of B. A minus B is A plus the opposite of B. Every subtraction can be turned into an addition. Frequently, addition is an easier way to do stuff. Every subtraction can be turned into an addition. You've seen this. Sometimes that's something to kind of look at when we look at the basics. You have done it. We have done it. We've gotten to here. We're not done. There's a lot here. There's a lot to say. I can't get into everything that there is to say, guys. I don't think anybody can teaches this stuff. But you kind of point to as much as you can. You're going to see the challenge in any endeavor that you do. Practically any endeavor that you do. You're not going to know everything. You're not going to know everything. You're not going to have the time to do everything. To know it. But you know what you're going to do. You're going to work hard. You're going to learn as much as you can. You're going to have fun with the stuff. And we're going to be okay. All right. I'm being made fun of because I talk with my hands. If you're from the Mediterranean, you got to talk with your hands. There's no other way around. All right. So we're talking about this, guys. We're looking at this stuff. And we got all this. So now what we're going to do? We're going to do what we usually do. Each one of these separately, you guys, I got a question to ask you. Here's a factor. Here's an item. Let me call it an item. Here's another item. Here's another item. Here's another item. Here's yet another one. Here's yet another one. Great. There's 6 of them. Am I going to distribute again? Am I going to take this guy and distribute once again? Why on earth would I do that? I'm not going to do that. I know there's addition or subtraction right here. I get it. Everybody gets it. We got all this. I get it. Addition or subtraction, yeah. But not in here. In here, there's no addition and or subtraction going on. In each one of these, in fact, there is no addition and or subtraction going on. In none of them. If there's no addition and or subtraction present, do not distribute. Do not distribute. Let's see what we got. See where it's going to go. Well, okay. Didn't we just say numbers with numbers? That's x to the 1, that's y to the 1, x to the 1, y to the 1, x to the 1, y to the 1. I think, okay, we've been down this path, guys. That's z to the 1. I don't know if I needed to do that one, but here's z to the 1, here's z to the 1, here's z to the 1, whatever. Let's go. Do what I did in the past. Don't distribute. For each one of these 6, no distribution. 5 times 10 is 50. X to the 1, x squared, that's x to the 3rd. Y to the 1, y to the, so 1 and 2, 3. 1 and 3, 4. The z, there's nothing there. I mean, there's nothing with it. Do the same thing here. 5 times negative 50, negative 250. X to the 1 times x to the 1, 1 and 1 is 2. Y to the 1 times y to the 1, 1 and 1 is 2. 5 times 9, 45. X to the 1, y to the 1. Negative 9 times 10, negative 90. Z to the 1 times z to the 1 is z to the 2. The other guys just stick around for the ride. Let me just see where I have gone here. Make sure, okay, yeah, Okay, just make sure I didn't do anything wrong here. Forgive me, I did do something wrong. Z to the 1 is z squared, x squared, y to the third. I think we're okay. There, that looks okay. Let me just make sure here. All right. And then over here, negative 9 times negative 50 is positive 450. X to the 1, y to the 1, x to the 1, y to the 1, z to the 1, x, y, z. Right here, negative 9 times 9, negative 81, z is, all right, it's not, and there you go. Here it is. So there's a lot more there, guys. I think some pretty decent coverage of this in the do's and don'ts. We had, there was an issue yesterday when I tried to, try to take this. There's a lot we just don't know. I mean, there's a lot that we're struggling with trying to make this stuff work, and some of the equipment we're not used to and stuff like that, and some other stuff. And but I've got some real outstanding help here. I've had people help me out to really get this. Get this working. I mean, at school and elsewhere, I've just had a lot of good help. So, so there it is. You got all this, and there's your final answer at the end of this. And like I said, I got good coverage of this in the do's and don'ts, and in some of the algebra stuff. And I'm gonna leave it for you guys for my physics classes at UWM. If you guys want to like look at this to kind of enrich yourself again, look at some of the stuff, look at the do's and don'ts, look at some of the basics, because it's easy to forget stuff. I claimed to know math pretty well a long time ago, and there were like simple mistakes I was making that I should have known better on. I needed somebody to kind of walk me through it a little bit. So there's nothing wrong with looking at this stuff for anybody. So for my math classes and physics classes, or any classes anywhere, I hope this is of use to you guys. There's stuff you tend to see later in different classes. I don't want to make a real big deal out of it, but just, I mean, even the classes that I have right now, the math class I have, even if they don't go into some of the work associated with Pythagorean theorem and stuff like that, I might want to just quickly say something like that, because you do have it in various math classes and stuff. I may say that very quickly for everyone's personal enrichment, for my MATC students and for my UWM students. I think it's not a bad way to go. Okay, so there it is, guys. You've got it. Let me get rid of this stuff. I'm going to get hold some different rags here too, guys, to actually be able to get this thing cleaned up pretty well. Just might as well. I mean, it's a basic thing and it occurs enough. Now again, what I'm about to show you guys, for those of my students in my intermediate algebra class, you're not going to need to know this one thing I'm about to show. But if you take another class or a physics class, engineering class in the future, or there's some other math classes where they talk about like the physics in everyday life and the mathematics of everyday life, it's good to have some trigonometry under your belt. I'll just say a little bit right here, and maybe go into this in some other, probably within some more specified context later on with other people. I might just do it individually. At that point, maybe a little more individually for my UWM classes and for my MATC classes. I might just separate that out a little bit. But right now, for about a 5-minute presentation, I don't think it hurts anybody. I think a lot of you guys that are taking the intermediate algebra, you guys are going to be taking that. You may very well want to be taking a higher level class eventually. So I just think it's good for you guys to have that under your belt. What I'm about to show here really quickly. And so, see how it works out. A little extra doesn't hurt us, I guess. on that. And the people who are taking physics, you got to know this anyway at some level. I'll be a little more specific with you on that stuff as circumstances call for it, I guess you could say. All right, guys, I hope the audio here is pretty decent. I think the visual aspect is okay. And let me just say something really quickly here. There's like a famous formula that appears everywhere. So I'm just going to throw it out just since I'm doing some review here anyway. Might as well just throw something in here as well related to this. So let me see what I have here. All right, guys, there's this like really famous formula attributed to Pythagoras, the great Greek mathematician. I'm sure it predates him. Ancient Egypt had it, I'm sure, in Babylonia and stuff like that. There's a lot of places. The Greeks were really cutting edge in much of their mathematics. This formula, however, was not really on the cutting edge. It was probably around well before the Greeks were looking at it. They did other stuff that was definitely cutting edge, but this wouldn't have been one of them. There's great mathematics elsewhere as well, obviously, throughout the world. Some of it known, some of it not known. So a lot of brilliant people that have always been around, and frequently, you know, so sometimes people don't get the credit that they deserve. That happens quite a bit, you know. When we look, if you had, I'll try to be quick on this. You know, quickly throw this away is what I'm going to do right now. Hold on. They say basically if you got a right triangle, a triangle with a 90-degree angle in there, I think it's going to help you guys know this. And regardless of whether you see it, this stuff happens, well, I'll talk to you more about it when the time comes, I guess you could say. So, I'm going to be throwing baskets here all day. I mean, so we'll see what we can do. If this is A, and this is B, and this is C, and I absolutely cannot stay on this marker, but okay. So this is A, you guys, and this is B in length, and this is C, and that's a 90-degree angle. There's a number of ways to prove this. There's a fascinating proof of this. Maybe that's something for another lecture, guys. Hope I get to see you guys face to face one of these days, and we can work on this thing and figure out what we're doing. But the square of the length of the longest side, the square of the length, they call it the hypotenuse. The hypotenuse is opposite the 90-degree angle. The other two angles are smaller than 90 degrees. The square of the length of the longest side equals the sum of the squares of the two legs. So if you square root both sides, you square root c squared, you get c, and you get something like this. This right here, I'm not going to go, like I said, I don't want to beat this up too much right now. You know, I got other stuff I want to do with the intermediate algebra guys, but I mean, look, there's 1, 2, 3, there's 3 items up there. I can solve for any one of those 3 items. 1, 2, 3, I can solve for any one of those 3 items. Just get them by themselves. Get one of them by themselves, and get one of them by themselves, and then square root the quantity that's on the other side. If this angle right here were theta, keep it pretty basic, I guess you could say. They got these trigonometric functions known as the sine, they call it sin. The sine of theta, the cosine of theta, and the tangent of theta. The ratio of the leg opposite the angle compared to the hypotenuse, A over C, is defined as the sine of theta. The ratio of the adjacent over the hypotenuse, the side adjacent to the angle over the hypotenuse, is called the cosine of theta. And the rise divided by the run, the opposite divided by adjacent, is called the tangent. if you wanted to find what theta was, you'd have to find the inverse sine, the inverse cosine, the inverse tangent, and calculators do that. You did that some other time. Anyway, what's important here is, let's say you know what C is, but you don't know what A or B is. If you multiply by C on each side, that leg, the leg going vertical, is C times the sine of theta. The leg going horizontal, if you multiply by C on each side, that's B, is going to be C times the cosine of theta. So there's kind of a handy way to find out what the legs are if you know what the hypotenuse is. Okay. I don't want to get big time into this. I'm not going to stop right here, you guys, but at least for now, at least for the algebra guys right now, but at least something you need to know this. I mean, down the road you're going to encounter it, and we'll talk more. I guess we'll look at things as we need to look at them, I guess. For the physics guys, this is kind of just the beginning of the stuff you want to know. This is huge. Albert Einstein used this formula for his theory of relativity. What this ancient formula talks about, Einstein used in his theory of relativity. This formula gets used when you're talking about complex analysis, dealing with complex numbers. This formula gets used, in some sense, even in electrical engineering. Really? That? Triangles? Triangles, electrical engineering, triangles, Einstein's theory of relativity? Yeah. It's there. Anyway, want to talk to that. I figured since we've gone that far, hey, what the heck? Bring it up a little bit. I want to talk about it a little bit. All right. This is this. I mean, this is what we're talking about here. I guess generically for convenience and for no other reason, I guess you could say, we said what we said here. Now let's go to intermediate algebra. A little bit, some of the aspects of intermediate algebra. And this is going to help anybody. You don't got to be in a class to know what you need to know. Math is math. I don't care if I'm teaching this class on the other side of the world and I'm speaking another language on it. The mathematics is the mathematics. Okay? So let's see what we can say here. They've got this practice exam. We'll say practice number one. I'll call it just practice number one. Practice, it's old. For some of you guys that had me at UWM in some of the classes, I got old work that I say old work, old review. Old work, good review though. There's some good review there. Practice, this is a bit on the old side, but it doesn't matter. Practice number one. Sounds good. I may have to change my markers, guys. Some of these markers are not the greatest. This one's good, but it's about to go. So we'll figure it out. Okay, let's see what we can say, guys. Let me run through these. No matter how fast I go, you guys can always slow it down. And this is the advantage, I guess, of getting filmed as opposed to not getting filmed, right? I mean, so practice old number one. Let's take a look at it. Okay, let's see what I can say here, guys. They gave, now again, I've got this, I'm doing this now, and I haven't posted this as I'm speaking right now, but in the next few weeks I'm going to. This is going to be posted in both places, at my UWM work and at my MATC work. I was given permission to do so because it's my work. I'm using work that other people have done, some brilliant work other people have done as far as the problems that they're asking, and I'm doing the actual, I'm just doing the actual exposition of what it is that you need to know on that. So I was given the green light to go either way, to put this at the UWM site that I have and also at MATC. So I think I'm going to do that. I think it doesn't hurt to look at it. Do what you want to do, guys. I'm going to be giving you a lot of information that, and some of which you already know it well enough. You don't need to burden yourself too much. Take as much time as you have to get this right. I'll try to make this reasonable for all parties involved when we're trying to do this. Okay. They talk about various things here. Let me, for it, the way it's going to be posted is going to be the intermediate. It's going to say intermediate algebra online review for exam number 1. I just said old number 1, but if you look at it, it's going to, and the answers, all of the answers are in the back, like start to finish. And some of these are like, some of these are like 80 questions long, 80 problems long. I don't know if I can do all of these, given some of the time constraints I'm dealing with, but they're all here. All the answers are in the back, and they're going to be posted onto the appropriate course management system. For UWM, it's going to be on Canvas. For MATC, it's going to be on Blackboard. So you're going to have it there and be able to look at it. They're talking about different things you can say here. I did not bring my glasses, so I'm going to probably have to get about 20 feet away to actually read what I'm doing here. They are asking us, are these two things equal? You got to say if it's true or false, for example. This is problem number 2. This does not write well either. I literally got about 100 markers, guys. Unfortunately, about 90% of them don't work. Just kind of look and see if actually stuff writes okay. I think it's going to be okay. I'm going to look on the board too, guys. So if you got, for problem 2, a little bit better, I think. And I'm going to stick around a little bit because a lot of these are very similar, guys. And I think when you see them, they're asking you, is this true? Well, if you multiply anything by 0, you get 0. But if you divide something by 0, it approaches infinity. I don't want to get into this. I don't want to get philosophical about the whole matter or anything like that. But dividing by 0 is undefined. The smaller the number is that's in the denominator, and 0 is about as small a number in terms of absolute value as you're ever going to get. In fact, it is the smallest number in absolute value. Dividing by 0, dividing by any number that has a small absolute value, gives you a magnitude that's huge. So this thing goes toward infinity, or negative infinity in this case, depending on how you're approaching 0. We're not going to get there. In terms of magnitude, this thing's going toward infinity. This is undefined. They're not equal. To say they're equal is false. And there's another problem. Problem number 1 looks just like this, so I don't need to do it. You guys can look at it in my notes and say, okay, he's got some of the answers here. They did a pretty good job here. On a few cases, they might have given the wrong, they might have written down the wrong answer. We're human. We do that. We make mistakes. When we were doing some of the taping yesterday, a couple mistakes were made, so we had to come back at it again. That's a human thing. We make mistakes sometimes, but we do our best, and there are consequences. Hey, we've got to look at it again. It's not something that my mistakes are my mistakes. Simple as that. And I got to make it right. I got to take responsibility for it, and that's what we're going to do. We're going to take responsibility for our mistakes. So if they did something wrong, we'll try to correct it to the best of our ability. This is problem number 1. I'm sorry. Problem number 1 looks just like that. Problem number 2 is what I just did right here. They are talking about different things here for problems 3, 4, 5, and 6. Let me talk to you a bit about it. Again, we're in the same place here. They've got the real number system. So the real numbers. So hold on one second, please. So the real numbers break up into 2 big categories. Now the real numbers are everything on the number line, guys. They're saying some stuff. They're saying a few things here, guys, and I'll talk about it. Well, if you want to take the number line, okay, his marker's actually pretty good, guys, you know, surprisingly. Yeah. The other ones are garbage. Some of the others aren't that good. All right. If you were to darken everything in the number line, if you were to darken everything in the number line, those are all the real numbers. Positive numbers, negative numbers, zero, decimals, fractions, decimals that go on forever and repeat, decimals that go on forever and don't repeat. You name it, you name it, you name it, the real numbers cover everything. Now, there's two big subcategories of the real numbers. There is the rational numbers. Let me stop right there. What does that say? It says ratio. It's a ratio of two integers. There's the rational numbers, and there's the irrational numbers. The two together make the real numbers. The two by themselves, each one of the two by themselves is not enough to encompass the real numbers. There's an infinite number of rational numbers, there's an infinite number of irrational numbers, but you need them together to have the whole number line. Otherwise, there's holes in the number line. I said ratio. I've got to sort of put the horse, the carriage in front of the horse when I do some of this stuff, you guys. So, have here I'll clean this up a little bit later, guys. There's these things they call the integers. You almost got to go backwards here. Like I said, you got to put the carriage in front of the horse. The integers are numbers like -5, -4, -3, -2, -1, 0, 1, 2, 3, comma, dot, dot, dot. It's going on forever. They are a whole piece of a number, either 0 or negative or positive, but they're a whole piece of a number. Those are the integers. The rational numbers are a ratio of two integers, A and B. Anytime I get a ratio of two integers, that's called a rational number. What does that mean? Isn't 2 an integer, according to what I just said? Isn't 3 an integer? What's 2 divided by 3? A ratio of two integers, like 2 divided by 3, that works. 2 divided by 3 is 0.6, going on forever. It doesn't end. Aren't those irrational numbers? No. It can go on forever, not end. And if it's predictable like this, it's a rational number. It's a rational number. So it's a ratio of two integers. Ratio of two integers. What if it was this? Negative divided by a positive. Anytime, I guess it's a good place to kill a couple birds with one stone, you guys. If you've got two positive numbers, divided, you do a division with two positive numbers, that would be the same as the opposite of one divided by the opposite of the other. In both instances, if you've got the same sign going on, you've got 2/3 implies positive answer. Negative 2/3. Negative 2 divided by -3, that also implies a positive answer. If you've got -2/3, you got a negative divided by a positive, or a positive divided by a negative. It's a lot of stuff to say, guys, but you got it here. I'm going to get into this a little bit more. I'll get more into this if we need to. But these are the rational numbers. A ratio of two integers. Underneath the rational numbers, there's this category of numbers called the integers. those are also rational numbers, but they're a special category. It's like me saying every Mustang automobile is a car. Yeah, it's a special kind of car. Not every car is a Mustang, but every Mustang is a car. Every integer is a rational number. Not every rational number, though, is going to be an integer. But every integer is a rational number. Then they break it further, I guess you could say. Ran out of room here, guys. You got the whole numbers. No negatives allowed on that one. They're integers, but no negatives. So you got 0, 1, 2, 3, ... Whole numbers. And here we got the natural numbers. And that's the counting numbers. So these are all under the category of rational numbers. Every Corvette is a car. True. Every car is a Corvette. No, that's not true. That's not true. Every child is a human being. Yes. Therefore, every human being is a child. No. I mean, it depends how you want to define child, too. That's another aspect. Every tiger is a cat. True. Every cat's a tiger. No. So, kind of watch how that plays out. The irrational numbers are numbers that you cannot write as a ratio of two integers. Some famous numbers there. There's the beautiful number e, the base of the natural logarithms, which is approximately 2.718281828, something like that. And it goes on forever. Pi is a famous one. Most of the square roots, most of the roots, etc. There's an infinite number of these now. These are the irrational numbers. These are the irrational numbers. So they kind of talk about that. So they kind of go down the line on this one. They sort of go down the line on this one. They said, for problems 3, 4, 5, and 6, all integers are whole numbers. No, all whole numbers are part of the integer family, but not all integers are going to be whole numbers. No, that's not true, because -5 is not a whole number. A whole number is this. False on that one. All integers are natural numbers. No, all natural numbers are integers. All of these fit under the category. The Mustang fits under the category of a car. Or the Ford brand. All the Ford brands are Mustangs. No, they're not. So no for that one too. All irrational numbers are rational numbers. No, there's a big, this is a yes or no right here, guys. It's like me saying to you, every cat is a dog. No. In this animal shelter, there's only dogs and cats. Therefore, every dog is a cat. No. Every dog's a dog. Every cat's a cat. The rational numbers, they are mutually exclusive. They're mutually exclusive. Every rational number is not an irrational number, ever. Every irrational number is not a rational number, ever. All whole numbers are integers. Yes. Every one of these, 0, 1, 2, 3, fits under the category of integers. Yes. So for 3, 4, 5, 6, all integers are whole numbers. No. 4, that was 3. All integers are whole numbers. 4, all integers are natural numbers. No. 5, all irrational numbers are rational numbers. No. 6, all the whole numbers are integers. Yeah, that's true. That's true. All right. Kind of run around with this a little bit, guys. There's more here. We could, cross bridges as we need to cross them. But let me try to see some ways I want to talk about some of this stuff. There's a couple other things I want to kind of talk about. I think get us under control. This one, again, whether you're taking a physics class or an algebra class or an advanced calculus class, a lot of the stuff I'm showing you, you always got to know it. So don't ever worry about that. I mean, it's always going to be worth your while when we're talking about something like that. And again, they've got the answer here in the roster. They've got a lot of the answers here in the roster, you guys. So I'm going to kind of jump ahead a little bit and kind of go from there. Everything that's here, the answer key has this, and you're going to have it in the printouts that I've given to you guys on there. So let me kind of jump ahead to things that are a little more difficult, maybe. Let's say we go to problem 11 pretty soon, and let's see what I want to say regarding that. Before I do, let's talk some more, I guess you could say. Your phone's taping, right? I mean, the phone, it's working, okay? You see it or what? I had a taping adventure yesterday, guys. Like I told you, I don't want to repeat it. So I want to make sure you guys get what I'm trying to say to you. Not that I know a whole lot, but whatever little I know, I want you to get it. Okay, good deal. So all right, guys, see what we can say here. Trying to think. I'll wait for this thing to dry off a little bit. Is there any, there's something there you can dry it off with. Give me 1 second, please. All right, guys, there's some, here we go, more do's and don'ts, right? If we can look at some of this and say, there's this idea of order of operations. There goes this marker too, I guess. Okay, guys, it should be pretty, let's see if it's pretty visible. Yeah, it looks visible. Order of operations. What's going on here, guys? With order of operations, they are telling you the first priority is brackets and parentheses. Brackets and parentheses. Whatever's in brackets and parentheses, if they actually give you answers, so to speak, they actually give you answers to what's in the brackets and parentheses, you have to do everything that's in there first before you start moving around. There's a lot of ways you can do this. There's a lot of subtlety to the whole process, okay? But we're not going to worry about that. We're not going to, At least not right now, at least. So what we're talking about, brackets and parentheses have the highest priority. You take care of what's in there first before you go further. After that, you do powers, roots, exponents. You know, I don't want to split too many hairs on this, guys. But powers, roots, exponents, that kind of thing comes second. Powers, roots, exponents comes second. Brackets and parentheses comes first. After that, after that, multiplication and division come afterwards. After that, addition and subtraction. Well, which one gets done first? As you go from left to right, if there's no brackets or parentheses, do whatever you encounter first. If you go from left to right. You read the English language from left to right, you will move from left to right, doing it according to the scheme that we have here. You will go left to right. So, multiplication, division, so order of operations, brackets and parentheses, powers, roots, exponents, multiplication and division, addition, subtraction. Some other, for order of operations, some other do's and don'ts, guys. If they're talking about multiplication, if they're talking about division, if they're talking about addition, if they're talking about subtraction, for any real numbers in the universe of real numbers, so to speak, for any real numbers, you guys, if you multiply any two positive real numbers, you get a positive answer. If you multiply any negative, if you multiply any two positive real numbers, you get a positive real number for an answer. If you multiply any two negative real numbers, you get a positive real number for an answer. If you multiply a positive times a negative, or a negative times a positive, what's the moral to the story? If you multiply two real numbers that have the same sign, both positive or both negative, you get a positive answer. Any two real numbers. Any two real numbers that have the same sign, they're both positive or they're both negative. If you multiply them together, you get a positive answer. Any two real numbers that have opposite signs, when you multiply them together, you get a negative number. Division is completely analogous to that. If the signs are the same in a division, both positive or both negative, you get a positive answer. If the signs are opposite, you get a negative answer. If the signs are opposite, you get negative. Same thing. If you add two positive numbers, guaranteed the answer is more positive. If you add two negative numbers, guaranteed the answer is more negative. If you add a positive and a negative, or a negative and a positive, man, that's an interesting story. It could be zero, it could be negative, it could be positive. It's a tug of war. The number with the bigger absolute value determines the sign of the answer. Subtraction. I'm going to make your life easy as far as subtraction is concerned. My advice to you is, if they ever tell you to subtract, you add. Remember that A minus B is the same as A plus the opposite of B. Whenever in doubt, add. There's some more do's and don'ts for you. It's going to help you anywhere. It's going to help you in physics. It's going to help you in engineering. It's going to help you in pre-engineering classes. If you somehow, whatever, if you somehow draw a blank somehow, okay? You're going to be fine. If you draw a blank, you can look at the basics and say, okay, let me build myself up. Let me get back on my feet with this stuff again. That's some of what this is. That's some of what this is. That's some of what that is. So it's looking pretty good. Looking pretty good. So they go into this a bit. They don't, they say a few things. I guess they say enough that I should just kind of, I'm just going to do the best I can do, I guess. How about that? I mean, I'm gonna look at what they're doing. I'm going to problem number 11 on the same practice exam number 1. Okay. So, how long